In this section, we're going to introduce our first deep learning model that's going to be used for unsupervised learning, autoencoders. Now let's discuss the learning goals for this section. In this section, we'll start off with a review of non-deep learning based techniques for data representation, such as PCA, and how we can use that to condense our original data set into a smaller representation of that same data set. After that, we will discuss how autoencoders leverage neural networks to also come up with lower dimensional representations of our data. And then finally, we'll discuss a bit on how to describe those use of trained autoencoders in order to actually generate images. Now, autoencoders will be our first time looking at deep learning from an unsupervised learning vantage point. Now, the goal of autoencoders is going to be to use those hidden layers in our neural networks to find a means of decomposing and then recreating our data. And we'll see how this is done in just a bit. And this proves to be powerful for things such as dimensionality reduction and fighting that curse of dimensionality, as we've seen in prior courses when we were working with PCA. With that, this dimensionality reduction can be powerful for pre-processing for classification and identifying only the essential elements of our input data while filtering out the noise within our data set. Now, as motivation, let's say we want to find whether two images are similar to one another. So we have two pictures here, each of a kangaroo, and we want to know whether each of these images are similar to one another. Now, one option, and I'll say right off the bat that we probably don't want to do, is to look at the pixel-wise distance between these two images. So if we look at the image to the left and we look at the pixels there in the top right corner, compare it to the pixels in the top right corner of the right image, we see that these two are clearly not the same. And we can even see this with our own eyes, that these are very different if we were just looking at these particular pixels. And the goal would be, and our problem here, is that if we just look at the pixels as a whole, we'll only be able to see the placement of the color scheme, of the brightness, etc., and not the actual content of our image. So the goal would be to find some type of representation that captures that actual content within the image. So if we think about the image here to the left, we're looking at brown kangaroo fur, kangaroo ears, a kangaroo nose, a beige background, and those are going to be content within that left image. In that right image, we have brown kangaroo fur, kangaroo ears, kangaroo nose, and a green background. So many similarities and maybe just a difference in background. And the idea would be that with autoencoders, and if we think about what we've learned with deep learning, how it's able to find each of those features that make up the image, with something like autoencoders that leverages these deep neural networks, we should be able to capture these essences. Now, before getting into the actual method of working with autoencoders, I'd like to introduce here a business application for what we just discussed and how autoencoders can be used in business practice. If we think here of electronic components within a production line, some defects might be imperceptible for the human eye or difficult to scale given if we're looking at images of each of these chips and the amount of pixels in each of these images, and we have to look across millions of chips, may be too difficult to scale. We may want to then reduce the dimensionality of those pixels so we can look at these defects at a lower dimensionality when we're comparing whether or not they're similar to one another, whether or not there's a defect. So one approach to this, to being able to detect these differences at scale, would be to use PCA to reduce the dimensionality of our features, which here are going to be pixels, so that each component is some linear combination of our principal components. So we start off here with a pixel vector. It's here going to be RGB, so we have the 3 channels, and for each one of those channels we have the height and width. We use PCA, and again we're able to create a linear combination of our principal components, if you recall from courses past, and reduce the number of dimensions that we are working with. Now, just a quick reminder how PCA works before we get into autoencoders and to motivate autoencoders. PCA works in reducing dimensions of our original data, and the goal within PCA is to find the dimensions that capture the most variance from our original data. So as an example, if we're working with just 2 dimensions, you can think of this again as just 2 features. The directions of the arrows will represent the principal components, or the directions representing the most variance within our data. And the lengths of these arrows correspond to the amount of variance in the original data that is explained. So we see the diagonal pointing to that upper right, accounting for more of our overall variance, the one pointing to our upper left. And we see that each one of these arrows will actually be composed of a combination of both x1 and x2. And now just saying which single axis accounts for the most variation won't be what we're doing, but rather some combination of those, creating new axes coming from that x1 and x2. Now, there are going to be limits to working with PCA and why we'd want to move to something like autoencoders. The main thing is that learned features will have to be some type of linear combination of our original features. When in reality, there may be some complex nonlinear relationship between those original features and the best lower dimensional representation of those features. And finally, how we define the best representation can be different depending on what our problem is. So that closes out our video just motivating the use of autoencoders. In the next video, we will pick up and dive into how autoencoders actually work. All right, I'll see you there. So autoencoders are going to be a neural network architecture that will force the learning of some lower dimensional representation of our data, and that's commonly used for images. So the way that autoencoders work, step by step, is that they will have that same value as both input and output, as we see in the image. We'll then feed this input through our encoder network, represented here as that densely connected nodes in blue. From this encoding step, we're going to be able to produce the lower dimensional embedding of our original data. And that's going to be what we're actually looking for, right? That lower dimensional representation of our data. And that will be here in the middle of our network. And then finally, that embedding will be fed through the decoder network, which we have there, through to our final output, which again is going to be the same as our input values. And that decoder portion is meant to go about creating a reconstructed version of that original data. And once we have that reconstructed version of the data, we can go about computing the loss between that reconstructed version and that original input and use that to train our actual network. So we take that loss function, as we do with any neural net, and use it to update the weights within our network. And that's going to be that feed forward and back propagation steps that you're already used to. And the result will be that in that middle portion, given that if you've noticed the nodes be shrinking in, so we start with 3 nodes, then 2 nodes, and it could be 100 to 10, whatever it is, as those amounts of nodes shrink, in that middle, and then again it shrinks and then expands back to that reconstructed version in the decoder step. In that middle, where we have just 2 nodes, we're going to have that lower dimensional representation of our original data. And we can use an autoencoder to find image similarity because we feed two images through the encoder network, and we can calculate the similarity score of their latent vectors, of this lower dimensional representation. So that allows us to actually see at a version that we'd be able to scale because it wouldn't require as much memory, how similar two images are. And we can always use that decoder portion of the network to map those vectors from our lower dimensional space to the full dimensional space of our images. The point being that this allows us a means of compressing and then decompressing our data. Now, another use of the decoder model is to actually work as a generative model. And in order to properly do this, we would probably want to actually work with variational autoencoders, which we'll discuss in the next lesson. But even with variational autoencoders, this isn't going to be commonly done, this generative model, due to the fact that in order to get reasonable results, some deep convolutional architecture is generally going to be required. And even with that, generally speaking, the results of that image generation will generally be inferior to that of GANs, which we'll learn not in the next lesson, but in the lesson afterwards. So autoencoders can have a wide variety of enterprise applications. They can be powerful for pre-processing and reducing the dimensionality of our data prior to learning some classification model. It can be powerful for sending information in a compressed form, as well as retrieving such information. It may be used for anomaly detection, as we discussed with the chip images. It can help with machine translation, as we're generally working in very high dimensional space if we're doing machine translation. It can be powerful for image-related applications, such as generating images, denoising, or taking fuzzier images and sharpening them, as well as processing and compressing, as we discussed. And for drug discovery, popularity prediction of social media posts, and sound and music synthesis, it can help find the key components that are key to each one of these different domains and help identify those key components that may be key to the model in drug discovery, popularity of a social media post, or sound and music synthesis. One last note. While most autoencoders will use deep layers, autoencoders are often going to be trained on just a single layer, each for the encoding and decoding step. And an example of working with a deeper network is going to be using sparse autoencoders, which essentially allow for those deeper networks, but only certain nodes will be firing within those networks. And this has been used successfully in things such as recommender systems. So just to recap, in this section, we discussed non-deep learning based techniques for data representation and reminded ourselves how PCA will use a linear combination of our original features to come up with a representation that maintains as much of the variance as possible from our original dataset. We then discussed how autoencoders work, with the encoder portion coming up with a condensed version of our data, which can then be reconstructed using our decoder network. And then finally, we discussed a bit how trained autoencoders can be used to generate images. And that's especially true using something called variational autoencoders, which we'll discuss in this upcoming video. All right, I'll see you there. In the next videos, we will introduce the concept of variational autoencoders, which will work similar to the autoencoders that we just discussed, except now that latent space, that hidden space that we're trying to represent, is going to be described by distribution rather than exact figures. Now let's go over the learning goals for this section. In this section, we're going to cover how variational autoencoders work and how we can come up with this new latent space represented by some distribution. And then we'll discuss variational autoencoder loss functions, and that will provide us with some intuition as to how variational autoencoders are used and optimized. Now, with variational autoencoders, we'll still be generating that latent representation, or again, that compressed representation of the data that encodes those similarities. And then similarly, we can reconstruct these to generate new samples. Now, some important features of variational autoencoders will include, rather than the data being represented by just a single set of vectors, the values of the data in that latent representation will now be represented by a set of normally distributed latent factors. And now, rather than the encoder coming up with a particular value, it instead generates the parameters of our normal distribution, namely the mu and sigma, or the mean and the standard deviation. And then using variational autoencoders and the fact that we are going to be sampling from a given distribution rather than some fixed values, we can actually generate new images. Now, the goal of variational autoencoders will be to generate images using the decoder portion of our network. Now again, starting off, our encoded latent vector will now be represented by some normal distribution. And the parameters for that normal distribution will be learned by the encoder portion of our network within this variational autoencoder, and then fed through to our learned decoder portion to produce the images. And a secondary goal that will come along with that is that similar images will be close together within the latent space. So as we'll see in our notebook later on, if we're looking at hand-drawn values between 0 and 9, the latent space for all of the zeros will be close to one another, for all of the 5s will be close to one another, and so on and so forth. So let's walk through the steps of how variational autoencoders will come up with this latent space represented by a normal distribution. The first step will still be to pass through a network with some bottleneck, so reducing the number of nodes, as we did with the regular autoencoders. But now at step 2, we're going to be learning a mu and a sigma for each value that are meant to represent a normal distribution from which values can be sampled. So for example, here we may end up coming up with the vectors that we see, which are for the mu 0.7 and negative 0.6, and then 1 and 0.6 for the sigma values. In the next step for our variational autoencoders, we combine these two values into one vector and add on some white noise with a mean of 0 and a standard deviation of 1. So using our example from before, we can come up with this vector at the end of 2.01 and 0.54, by adding the mean, that mu, plus the sigma multiplied by our noise term. And those are the vectors that we see here at the bottom that will tell us what is going to be some sample from our distribution. This randomly sampled vector is then fed through our decoder network in step 4, and we then can produce our reconstructed image. So that's how we walk through this variational autoencoder with the mu and sigma. In the next video, we're going to touch on a high level some of the math that makes the variational autoencoders work and are specific to this variational autoencoder in general. All right, I'll see you there. In this video, I want to start off by discussing the loss function of the variational autoencoder compared to that of what we would do with just the autoencoder. So our goal will be to reconstruct the original image as we did in our autoencoders. Now we know that a major difference is that the variational autoencoder will be reconstructing a vector drawn from a standard normal distribution. And with that in mind, we're going to have two components to our variational autoencoder loss function. First, we have what we had for the normal autoencoders, which is just the error measuring how far off our reconstructed image was from that original image. The second part of the loss function will be a penalty associated with generating vectors of the parameters mu and sigma that are both different from 0 and 1. So mu being different than 0 and sigma being different than 1. As our goal will be to balance between that low reconstruction penalty, as we did with autoencoders, while keeping our parameters as close to the standard normal distribution as possible. So this comes down to the pixel-wise difference between the reconstructed and original image for that first component. And in order to calculate calculate this, we can use a loss function such as mean squared error to see the distance between the reconstructed image and the original image. And then again, the second component will be the difference between the vectors produced by the encoder and the parameters of a standard normal distribution. So how do we go about calculating that second component of our loss function? For this, autoencoders will use something called KL divergence between the data that we generated and the standard normal distribution. So here we have, for example, our mu values versus a mu of 0. And then we're actually going to take the log of sigma. And if we think about our sigma, the ideal sigma would be 1. The log of 1 would be 0. So we're going to be comparing the log of our values versus 0 again. Since, again, the log of sigma is going to be, the log of 1 is going to be 0. And we use the log to ensure that we end up with strictly positive values, as a negative value for variance doesn't really make any sense. Now, the actual KL divergence formula will be what we have here, where e to the log of sigma minus the log of sigma plus 1 is going to penalize the sigma for straying from 1. And we can note if sigma is 1, then log of sigma is 0. And if we replace log of sigma with 0 here, we would see that this comes out to 1 minus 1 and is thus minimized at sigma equal to 1. And then for mu, obviously mu squared will be minimized when that mu value is equal to 0, because if it goes a little bit to the right to 0.5 or even up to 1, then mu squared would be 1. If it goes a little to the left to negative 1, again, you'll have a value of 1. So it'll be minimized when mu is equal to 0. And in regards to that sigma portion, we can somewhat see graphically, if we imagine subtracting that orange line from the blue line, that again, e to the x minus x plus 1, which is similar to our sigma portion that we discussed in our KL divergence formula, that again is going to be minimized at x equal to 0. Now, a note on KL divergence. It's not technically necessary to include this component in our loss function. But the reason that we do like to include it, though, is that it helps generate a desired latent space where visually similar images are going to be close together within that latent space. So as an example, what we have here is a variational autoencoder trained with 2 dimensions in the mu and sigma vectors. And because this is a generative model, we can scan the latent plane and sample points at regular intervals and actually generate corresponding digits given what we sampled for each one of these points. And as long as our sampled values are close within that latent space, within that lower dimensional space, which is represented by our mu and sigma, they will generate similar images. And that's why you see 7s up to the left and some 9s in the middle. None of these were actual images within our data set, but using our variational autoencoders, we were able to generate these randomly. Now, just to recap, that will close out our section here on variational autoencoders. We went through the basics of how variational autoencoders work and how they differentiate from regular autoencoders, and that they produce a probabilistic means of describing our latent space. And with that, we also discussed the loss function used and why adding on KL divergence to measure the distance from the normal distribution can be very powerful. Now let's take a look at some actual code as to how we can actually build out autoencoders as well as variational autoencoders of our own. All right, I'll see you there. Welcome to our lab here on autoencoders. In this lab, we're going to be going over dimensionality reduction techniques on the MNIST dataset, which is those handwritten digits that we'd seen in earlier notebooks. And we're going to perform dimensionality reduction using first PCA as a baseline, which we learned in earlier courses. And then, as just discussed in lecture, autoencoders and variational autoencoders. And with each one of these models, we're going to use the appropriate scoring metrics so that we can compare the performance across each. So a quick reminder of what the MNIST dataset is. That's going to be handwritten digits between 0 and 9. We'll have 70,000 different handwritten digits, all in black and white. And when we run this traditionally, we're going to split this into 60,000 training images and then 10,000 validation images. And this is such a common data set that it's actually built into Keras. So we pull it out from keras.dataset. We pull out the MNIST functionality. And with MNIST, we can call load data. Once we call that method, we get the output of our training set, xtrain and ytrain, and our test set, xtest and ytest. And we run this, and we can actually look at quickly the shape here. And we're working with 28 by 28 images. And if you recall, because it's black and white, this won't be three-dimensional. If it had RGB or some color scheme to it, then it would be 3 dimensions, such as 28 by 28 by 3. But here it's all black and white, so our pixels will all be on the grayscale, and that'll be 28 by 28. And if we look at just a single image, we can see that each one of these different pixels are going to be some number between 0 and 255, representing the light or darkness of each one of these different pixels. So this takes up a lot of space. I'm just going to clear that out. Now we want to make sure that they're all between 0 and 1. So we're just going to divide here by 255. And then if you think about it, the max number is 255. We divide by 255, the max number is now 1. We're going to use now PCA as a baseline with which we can compare against our deep learning models, which we'll do later on. So for PCA, we're going to have to treat each image like a row of data. So we're going to have to flatten out those 28 by 28 images. In order to do that, all we have to do is call that xtrain.reshape. We saw that the original shape was 60,000 by 28 by 28. We keep that 60,000 because we still have 60,000 different examples. And then we just take a product of that 28 by 28 here. That's 1 through, dot shape 1 through is going to be that 28, and then the second 28. np.product is the product of the two, so that will end up with 60,000 by 784. And then same for the test set, we'll have 10,000 by 784. And we see those results here. Now just a quick one-sentence reminder on how PCA works. So PCA will do a matrix decomposition of this data that we're working with to find the eigenvalues. And these eigenvalues will end up being the principal components of our data, or those latent features that describe the maximal amount of variance in the data. We've been talking about these latent features, that lower dimensional space that hopefully represents the important portions of each one of these different pieces of data that we're working with. So just to ensure that it's scaled, we already got it between 0 and 1, but we will just run the min-max scaler here. We call min-max scaler, which we imported from sklearn.preprocessing. We fit it on our xtrain flat, that flattened data that we just produced. And then we call transform on that xtrain flat. And now we have our xtrain scaled. Now the function that we're going to use for PCA, it's going to take in some data, and it will end up being this xtrain scaled to start at least. And we say the number of components, how much do we want to reduce our data set by? That's going to be something that we determine in the preset. So we can say we only want 2 dimensions, 5 dimensions, so on. We then, going into the actual function, are going to call PCA, and that model needs the hyperparameter of how many components do we actually want. We say that we want the number of components that we defined here above in the function. And then we have our PCA model that's been initiated. We then fit that model to our data set. by calling pca.fit on that x data that we pass here into our function. And now we have this fit PCA, we have that model fit to our data. And then we can print out here quickly after we run this, how much of the overall variance was explained with the number of components that we passed in through our function. So we say variance explained with, say, 2 components, and then we just print out the actual amount explained, and that's going to be done by calling that fit model, getting the explained variance ratio, which we'll show in just a second what that actually looks like, but that quickly is going to be the amount of variance explained by each one of our different components. We take that sum and we see the overall amount explained, where the maximum value, summing those all together, should be equal to 1. We're then going to return our fit model so that we can use that once our function has run, as well as our transform data. So that's going to be our data set reduced down to our new number of components, that new number of dimensions. So we're going to do this with 784 dimensions. So that's going to be all of the data. And when I run this, recall it's going to print out the amount of variance explained. I would want you to think to yourself how much of the variance should be explained. We run this. And with all 784 components being taken into account, all of the features being taken into account, we see that 100% of the variance was explained, which makes sense. Now, just to be clear on what this explained ratio attribute is of our model. If I run this, this is going to be an array that says, for each principal component, what is the marginal amount of variance explained? So the first component explained this much of the variance, the second one, this much, I believe it's around 0.09, then 0.07, and we can see that the length of this, given that our PCA model took all of the components, will be 784. And if we actually plot this out, we can take that cumulative sum across all 784 components, and that's what this cum sum does, for this entire array that we just printed out. And we can see how much of the variance is explained as we add on more and more components. And we can see that we need about 250 components to explain about 90% of our variance there. Now, for visualization purposes, let's try reducing it down the number of features down to 2. If we reduce the number of features down to 2, then perhaps with those 2 features, we can see whether or not we were able to group together where the 1s lie in those 2 features, where the 2s lie with those 2 features, with just those 2 features, so on and so forth. So we run this, and we get our output of both the model as well as our transform data. Now I'm going to get to this in just a second. That's just an example of how to explain what we have here. What we want to do is plot out each one of these numerical values that we have, 0 through 9, and we have those labels available to us. And for each one, we want to plot out in these new 2-dimensional space that we have, where each one of those points lie. So just to ensure that we don't have too large of a scatter plot, we're only taking the first 250 examples of each. Remember, our X-train has 60,000 examples. That would be quite a dense scatter plot. Then for numbers ranging between 0 and 9, including 0 and 9, if we say range 10 doesn't include 10, we're going to create this mask, which is just saying, does y-train equal that number where we currently are? So we can say here, let's just start off y-train equals 0, and we can see whether or not that exact example in our full array, and y-train is going to be of length, we'll just put that out, 60,000, right? So it's going to be for each one of the different examples. Is it labeled as 0? We're then going to mask our data. So this MNIST data 2, again, is the output from our function. So it's that 2-dimensional data. We're only taking the rows from that 2-dimensional data where our y-train is equal to the current number in our for loop. And then we're going to say, take just that first column. We only have 2 columns, only 2 features. And then we're only taking the first 250 examples. And then we're going to do the same thing to get our y data, or our second axis, by saying, again, I only want the rows where we have it equal to the y label specified. So starting off at 0, is it equal to 0? And then we want that second column. And again, only the first 250 examples. We then plot that scatter plot of the x data and the y data. We label it, we'll call that legend later on. And once we run this, we can see for each one of the different values whether or not they create clumps in this two-dimensional space representing that 0, 1, 2, and so on. And we can see, for example, the ones here in orange are already disentangled and grouped together on their own. We can look at the 9s, which are light blue here, and the 4s, which are purple, and we can see that those are fairly close to one another, which makes sense given the way that 4s and 9s are drawn. And you can continue to explore where groups were able to separate themselves out or where there seems to be some type of overlap. But we can already see that these latent features within PCA are learning somewhat how to disentangle our features, and perhaps a neural network could help even further in doing this. So now we want to score our PCA. Again, we're going to want to come up with some actual function to decide whether or not we are improving how well we are performing in regards to working with the PCA versus working with our network models. So the number that we're going to be using, the latent features, the amount of latent features we're going to be working with, here is going to be 64. So we call that MNIST PCA function that we defined earlier. We call 64 dimensions. We run this. We now have our model, as well as, besides that model, also the actual transform data. We're then going to take our X test flat that we defined earlier and scale it so it's on the same scaling that we used with the, this S was for transforming above here our X train. So we're using that same S to transform our X test. We're then going to use that PCA 64 that we just fit on our training set to transform our X test scaled. So that's going to give us X test flat in 64 dimensions. And then we're going to reconstruct that same image back to the original dimensionality, that 784 dimensions that we were working with. And we do that by calling PCA 64, which is our model, inverse transform on that X test flat 64 that we just produced, on that 64 dimension data of that we just produced by calling PCA 64.transform. So this is that reconstruction that we're trying to do. We're reconstructing our original image by reducing the number of dimensions and then going back to that original amount of dimensions that we were working with. We can look at the shape here, and as expected, given that we have the test set, there's 10,000 different samples, and reconstructed, they're back to that original dimensionality of 784. We're then just going to call this true and reconstructed, so it's clear when we call this into our model, and that's going to be our X test scaled versus our reconstructed data. We're then going to come up with the mean squared error of that reconstruction. So we just say true minus reconstructed for all the different pixels, and we just average out the total error that we have there. And we can call that on our now true and reconstructed that we just defined above. And we see that we have an average mean squared error of about 90.5 when you use 64 components for PCA. So that's going to be the baseline that we're working with. We see a mean squared error of 90.6. That closes out our motivation, building out that baseline. In the next video, we're going to start to work with autoencoders, a simple autoencoder, to see if we can do better than this baseline performance that we currently have, a 90.6. All right, I'll see you there. Welcome back to our lab here on autoencoders. If you recall, in the last video, we used PCA in order to reduce the number of dimensions down to 64, and then reconstructed our image, and then saw how far off our reconstructed image was from our original image. Now we're going to do the same thing, except using autoencoders and using neural nets. Now, so far, whenever we built out our neural nets, we've been using Keras, and from Keras we've been using the sequential API, where we just add on layers. And that's a bit of a simpler way of building out your neural nets. What we're going to introduce here is the functional API. And that's going to be fairly simple as well, and we'll walk through the steps here in regards to actually building out these complex architectures. And what it'll allow for is for more flexibility in building out your models. So if you think back to our convolutional neural net discussion, and we didn't have a notebook there, but if you wanted to build some of those more complex architectures, such as Inception or ResNet, you would have to actually use this functional API in order to build out layers such as with Inception, where you're concatenating a bunch of different types of layers together, or ResNet, where you want to bring along portions of the layer to further layers. You'll have to use something like the functional API. So it is worth getting a hang of as we talk through it here. So we're going to import from TensorFlow.keras this input and this dense layer, and we'll see how those are used in just a second, as well as importing model, which will be the key function in regards to the functional API within Keras. So the goal that we have when we build out our autoencoder will be to build out 3 different models. We'll have that full autoencoder, and that's taking that inputs, remember the inputs and the outputs would be the same, but taking that image and then ultimately reconstructing that image at the back end. So it'll be the encoder and decoder, where we deconstruct and reconstruct these images. We'll have the encoder portion, which is just the portion that will take inputs and try to bring them into that latent space, and then the decoder, which will take that latent space and try to reconstruct it. So we're setting our encoding dimension to 64, as we did with PCA, so we're going to have that latent space in 64 dimensions. We have to define, when we use the functional API, what our input is going to be. So this is just creating a blank tensor. And when we say a tensor, and that's where the word TensorFlow comes from, all we're talking about is an array in a certain amount of dimensions. So we're going to be using probably here 2 dimensions. One dimension is the number of samples. The other dimension, which we want to define the shape of, is going to be how many actual features we're going to have. If we kept it at 28 by 28, then for shape you'd probably put in 28 by 28, and then you'd leave out the 60,000 still. But we're initiating this blank tensor, and we're going to need this in order to define what the flow of our inputs to outputs actually are within the functional API. And then the reason why it's called a functional API, why we have the term function involved, is to become clear right here. We create this dense layer, and this is similar to the dense layer we saw before, where we call dense. We say what's going to be the dimension of that dense, how many hidden nodes are they going to be, and what type of activation are we going to use. And this portion right here is actually a function, and that function will be able to take a certain input. And all we have to do is say, as an input, we want these inputs that we defined here, that tensor. And then we only have a simple model here. So we're going, and this is just the encoder model, the encoder portion. In order to bring together all the steps, we call model, and we call the inputs and the outputs. And as long as the inputs and outputs match up, even if we added on a bunch more layers in between here, which we'll see later on, as long as the first value is able to reach that final value given our functional API and how we defined each one of the different steps, the model will be able to bring those all together. So we have our encoder model, which is this model that starts with the inputs and ends with the outputs from this encoded portion. We then are going to have our decoder model, which again, we're going to have our input defined. And this time, the input for the decoder model, if we think about the idea that it's taking that latent space and reconstructing our image, should be the dimension of that latent space. So it's going to be taking in vectors with dimension of 64, that encoding dim that we have here. We're then going to pass that through a dense layer. So we call that dense layer, and we want that dense layer to be reconstructing our image back up to 784 dimensions. We use the activation of sigmoid, and what we pass into that dense layer is in this parentheses, as you would with a function, we pass in the encoded inputs. And then our decoder model will just be, again, that model, and then saying what the input is and what the output is. And then to define the full model, first we're going to say what our outputs are going to be for that full model. And if you recall, our decoder model as currently constructed just takes in this input, which is just a blank tensor. Instead, we're going to define the input as the encoder model inputs. So it's going to move from inputs, pass out the encoder model output. So it's actually going to take that input that we defined, since we have that within the function. The output of the encoder model will then become the input for our decoder model. And then that decoder model will, by default, because of the way that we constructed the decoder model, output that final dense layer that reconstructs our image. And then our full model will just be the inputs, which are defined up here, and those initial inputs, and then those final outputs, which we just defined, which run from, we just created all the steps needed, runs from these inputs through the encoder model, then through the decoder model, and then outputs this reconstruction. So we run this, we now have our full model available to us. We set our model inputs equals inputs, outputs equals outputs. It's already what we did here. And then the steps from there in regards to compiling and fitting the model are the same as with the sequential API. We call compile, we define our optimizer, our loss function, and then what metrics we want to track. We're going to track accuracy. And then we're going to run this just for one epoch here on our xtrain flat. And then recall that our output's also going to be xtrain flat. Our input and output are going to be the same. We fit the model running through just one epoch. This will take just a second. And afterwards, we have the option here to actually just look at the summary. So we'll do full model.summary, which we'll look at right after this is done. In 3, 2, 1. We'll look at the summary, and we can see that it passes through that input of dimension 784 down to dimensions of 64, that being our latent space, and then reconstructs that image. Now, the way that Keras works is because we built out these smaller intermediate models, but actually trained them along the way, that encoder model that we fit into this full model that we defined up here has actually been fit to the data. So we can actually encode our image and output that 64 dimensional space. So we run this and we see we took our X test flat, which was originally 10,000 by 784, and reduced down the dimensions down to 64. And we can look at that and see that we now have those values which represent the different pixel values for, or that 64 dimensional version of the encoded image. And now that we have this available, our goal is to see what the reconstruction error actually is. So we want to use the trained autoencoder to generate reconstructed images and then compute the pixel-wise distance between that reconstructed image and the original image and see how we did compared to our baseline PCA. So we have our full model, which will both encode and decode our model. So we can just pass in xtest flat into our full model, which has already been trained to predict what the, if you think about, if we call full model.predict on xtest flat, it's going to try to bring that down to the latent space, so encode it and then decode it again into what should be exactly the same if it was able to do it perfectly. So all the decoded images will, when we run full model.predict, both encode it and decode it, so it's doing that reconstruction step here. and we get our decoded images, and then we can run that MSE reconstruction that we defined above to see what the actual error is on our decoded images compared to our original x-test flat. So you run this and we see that it did significantly worse. If you recall, we had around 95 for the mean squared error, and now we're at 346 about. We could have ran for more epochs as well rather than just one epoch to better fit the model, but even with 5 epochs, you'll see that it still does a bit worse. And in the next video, we'll see how instead of just using one hidden layer, perhaps we make our network a bit deeper and still run for a bit more epochs. And hopefully from there, we start to actually do better and perform better than what we saw with the PCA model. All right, I'll see you in the next video. Welcome back to our autoencoder notebook. As we saw in the last video, we built out our first autoencoder with the encoder and decoder portions of our model. And then with the reconstruction, we saw a fairly high error. And one of the reasons that we had this poor model was that we weren't really doing any deep learning. So what we're going to do here is first we're going to start off by adding on some extra layers. We're also going to run it for a few more epochs and see if we can get a lower reconstruction error than we did with PCA and see how much we're able to actually improve on that error. So again, our final encoding dimension will be 64, but this time we're going to be including a hidden dimension of 256. And this is going to work very similarly to what we just did. So this is another time to look through your practice through the functional API for Keras. We're starting off again with the input, and we just say the shape, and that's going to just initiate what type of tensor we want to pass through. And then we're going to have first that hidden dimension, which is just going to be a dense, so a fully connected layer. And we're going to pass into that fully connected layer with that hidden dimension of 256, our inputs. So we're just passing in our inputs. That will produce some output. We can pass that output through to another dense layer. So this is the hidden layer, and then this is the encoded layer. And this will take in that encoder hidden within the function. And this is the function itself. It's going to be another dense layer, now reducing it down to 64 nodes. And then to just create the model, we just say model, and we're going from inputs all the way out to the encoded outputs. And you don't have to write out this middle step as long as there's a connection between what's being input all the way through to the output. Within your model, all you're passing through is what the input is and what the final output is. And then we do our decoder model. And again, our decoder model should start off with that encoding dimension of 64, as it will be decoding now that latent space that has 64 dimensions. We're going to have another hidden dimension, so it'll take that next step up to 256 nodes, and then finally have the 784 nodes. And we can create our model that takes in the encoded inputs and passes out this reconstruction that we have here. And that's going to be our decoder model. Then just as before, we create our outputs by passing in the encoder model with the inputs as its input into the decoder model. That will be that final output to allow us to go all the way from the inputs to that final output that we have here. And then the full model, we can just say the inputs, which is these inputs, all the way out to these outputs that we just defined. We can look at that full model summary. We looked at the summary before. Now it doesn't show, it's just showing the different models, but now you see there's a lot more parameters that it's learning rather than just what we had here at 50,000. We're up to 217,000 because we have that 256 node hidden layer in between the inputs and our encoding dimension. So again, we have our full model, just going from inputs that we defined to the outputs we defined. We can compile it using the optimizer, the loss function that we care about, which metrics we want to track. And this time we're going to run it for 5 epochs. So we have the batch size equal to 32, so it'll run the gradient every 32 samples that we go through. And we're going again from xtrain flat as the input to xtrain flat as that output. Those two will be the same, and in the middle it'll be coming up with that encoding layer. So you run this, and this is going to be for 5 epochs, and it may take a bit of time, so I'm going to pause the video and we'll come back as soon as this is done running again. So now our model has been fit to, again, our xtrain flat and our xtrain flat, both as input and output. We can then call full model.predict on our test set. And again, that's just going to try to deconstruct and reconstruct, or bring it down to that latent space and then reconstruct that original image. So I'll run that and then again get that mean squared error of that reconstruction, passing in that new decoded image as well as the original x-test flat. And when we run that, we see that we get a score of 84.3. So it did better than PCA now that we've done 5 epochs and done this deeper network. Now let's see if we can improve even further. We notice that so far we're only using so many epochs. I want to see if maybe we introduce further training as we see the loss continued to go down and it hadn't plateaued yet, and the accuracy continued to go up. See if we can actually get a better performance as we increase the number of epochs. So this function that we have here will actually just be putting together all the steps that we have here above. So this, you can imagine, was just copied and pasted. So we're not going to go through that again into this function. And then we just say the number of epochs that we want to run through. And this is the part that's different, where for ion range, the number of epochs, we keep fitting the model to the training set. And recall that if we're not reinitiating the model, then what we are doing when we say only 1 epoch here for the entire range of epochs, it's going to pick up the training where the last one left off. So we'll see the results for just 1 epoch, for 2 epochs, for 3 epochs, and so on. And with that, every single time we'll get the decoded images, get our reconstruction loss. We will append that to this list that we have initiated up here. And we will say the reconstruction loss after each number of epochs is so on and so forth to see whether or not we continue to improve. So we initiate that function, and then we're going to run this now for 10 epochs, right? Number of epochs is the only argument we have available. We run this for 10 epochs, and this will take just a bit of time to run. We had the 5 epochs take X amount of time. This will take about double the amount. So we'll come back as soon as that's done running. So now we see the results. After 10 epochs, we were able to, for the most part, continue to reduce that reconstruction error, that mean squared error. We do see that it is not monotonically decreasing. At some points it seems to waver, but you see towards the end of 10 epochs we get it down to the mid-60s compared to that higher number that we had earlier. So those extra epochs, even though if we look at the accuracy score, it may not be improving that much, we do see that it continued to decrease that mean squared error of that reconstruction score. So that closes out our video here in regards to just working with the autoencoders. In the next video, we'll introduce variational autoencoders and how we can leverage those. All right, I'll see you there. Welcome back to our lab on autoencoders. In this video, we're going to be working with variational autoencoders specifically. And if we recall, variational autoencoders are specifically creating that latent space that's now going to be a mean and a standard deviation that signifies a normal distribution. And from that normal distribution, we will sample values and then pass those values through to our decoder to try and reconstruct our images. So again, just at a high level, the first neural network is going to be that encoder, where we're going to predict two vectors for each one of our images, where these two vectors will be interpreted as the mean and the standard deviation, and that can be sampled and used to pull out something from the normal distribution. The second neural network will be the decoder that takes the results of our encoder to reconstruct our original image. And then that entire system is going to be trained using backpropagation at each iteration. And if we recall with regular autoencoders, our input and output are the same. That's still going to be the case. And we're still going to try and minimize the amount of error when we're trying to reproduce that image. But now we're also adding on another penalization term if those two values are not going to be standard normal values. They're not going to be 0 and 1 for our mean and for our standard deviation. And that's going to be that KL divergence that we discussed in lecture. So we're going to import many of the libraries that we need. Many of these we've seen, some of them are new, and I'll touch on the new ones as we get into each one of the different portions within our code here. So recall that when we're trying to create our input from the encoded output, so that encoded output again is going to be that two-dimensional vector, and that vector is going to have a mean and a standard deviation. In order to create that, to transform that into input for the decoder, we take those means, add on the standard deviation, then multiply it by some random epsilon, where that epsilon is going to be some value sampled from the normal distribution randomly with a mean of 0 and standard deviation of 1. And that's how there'll be some variation in what's going to be output each time. So to create that sample, we're going to create this sampling function here, and we pass in args. Those args are actually going to be the mu and log sigma. It's going to be that output from the encoder. And we're actually going to add this on later on, and we'll see how we do this in Keras. Add this on to our actual encoder model at the back end of our encoder model so that we can produce a single vector. So we have our mu and log sigma. Those are our args. We unpack them here. We then set the epsilon equal to just a random value with a mean of 0, standard deviation of 1. That's going to be the default when you call random normal. And we want it the same shape as the mu so that we can add that on, and we'll see that in just a second, add that on to the mu plus the sigma according to this formula that we have here. We then set sigma equal to the log of sigma, e to the log of sigma, so that we just have sigma itself. If we recall the output, in order to ensure that it always is positive, we actually output a log of sigma, so now we need to transform that back into sigma. And then from there, once we have our mu and our epsilon and our sigma, we can produce random values by taking mu plus sigma and multiplying that by that epsilon, that randomly sampled value. So that's going to be our sampling function. Now we're going to create our actual encoder network. We have our inputs, same as before. We have our dense hidden layer, which is going to have hidden dim, so that 256 dimensions. So there's going to be some hidden layers. This will be a bit of a deeper network. It has its inputs, which we define here, that are going to be passed in. Again, we're using the functional API. Then that X is going to be used as input into both getting the mean as well as the log variance of our Z value. So we can use that X, and we wouldn't be able to do this as easily with the sequential API, and that's why we use a functional API. We can pass in the X to a dense layer here and a different dense layer here, so that we're outputting two different values with that input. And then to get that final output that we're looking for, we're going to call lambda, and that lambda function allows you to pass in your own created function, which we created above that sampling. So lambda sampling, and the input for that sampling is going to be this list, which is z-mean and z-log-var, and that corresponds to our ogs, which we were able to unpack up here into mu and log sigma. And then at the end of our encoder model, we pass in our model, the input's going to be input, and then the output, we're actually going to output 3 different values. We're going to output the z-mean, so that we can track that. We're going to output the z-log-var, and then we're going to output that actual z value, that actual sampled value as well. So now we've set up the encoder model. Then we're going to build out our decoder model. And that's going to take an input of the shape of our latent dimension, those 2 dimensions. We're then going to expand it, so similar to how we did with the autoencoder, where we first shrunk it down with the encoder and then we expand it with the decoder. Here we're doing that again, so we're expanding that out up to the hidden dimension first, up to 256, passing in those latent inputs. And then finally, that final output will be the dense 784 node layer, so that'll be the same dimensionality as our original image. And then we can just say that the model is going to take in those latent inputs, then pass out the outputs we defined by passing that into the model. And then to get the full model, we just do decoder model and we pass in the encoder inputs, but this time we only want as input that 3rd value. Recall that we actually are outputting in the encoder model 3 different values. What we really want to pass through into our decoder network is just that 3rd value, which is why we specify 2 here. And then once we have our outputs, we can create our full model, which goes from those inputs defined all the way up here in our encoder model to the outputs that we just defined up here. Now, just to take a quick dive in, we can look at our model, and we're going to look here at each one of the different layers that are involved. And within that layer, layers are defined a little differently than probably what we are used to in regards to working with our neural networks that have multiple layers, but rather the layers are the models that are being used. So we have the encoder input, and that's just going to have no weights that are being learned, and it's going to be of dimension 784, and none is just however many samples we want to pass in. Then in our actual encoder layer, outside just the input, we have the input being 784, and the output, as we discussed, being 3 2-dimensional vectors, one being the means, one being the sigmas, and one being those sampled values. And then within this encoder, still in layer 2, our first weights are going to be our dense layer, which gets us 784 by 256. Our next weights are going to be the bias term, which is just going to be 256 different weights. We're then going to get our actual mean values, which is 256 by 2, so those are the weights needed there. Our weights 4, now when I says weights 1, weights 2, weights 3, weights 4, that's not the number of weights. That's just representing weights number 1, weights number 2, and so on. The same way we did layer number 1 and layer number 2. And then we have our mean bias, and that's just going to be 2 values. And then we're going to have similar for the log variance with 256 and 2. And then in layer 3, we have our decoder starting off with the input of 2, output of 784, and we have all the intermediate weights similar that build up back to that 784 that we discussed. Now, again, if we want to start or go ahead and actually compile this model that we built out, we need to actually reproduce that loss function that we need. So I'm going to pause here now that we've built out the variational autoencoder, and the next video we'll talk through how to actually build out this loss function appropriately so that we can compile our model that we just built. All right, I'll see you there. So as discussed at the end of the last video, we're going to need a different loss function for our variational autoencoder. And the second part of that loss function, so we have the first one for the reconstruction error, which is the same as the autoencoders. The second portion, which is specific to variational autoencoders, is what we have here. And we discussed this in lecture, how we predict log sigma because predicting sigma directly is could result in a negative value and doesn't make sense to have negative variance. And then the fact that the cost function has two components, both of which penalize us for having results that deviate from that standard normal deviation. So if log of sigma is far from 0, we can use this portion e to the x minus x plus 1 being minimized at x equals 0. And that's equivalent to what we have here in the first portion of the KL divergence. And then the second part simply penalizes the mu value, that mean value, from being far away from 0. And then again, the other part of the loss function is just going to be that reconstruction error. So our exercise here was to actually create this loss function so that we can pass it through and optimize using this loss function, minimizing this loss function that we have. So we do this first by starting with the reconstruction loss. We're going to just multiply by 784 so that we're not working with the average value, but rather the full value, rather than the average over all the pixels. So we're just using this binary cross entropy. So far, we've been passing in that string as our loss function. But if you look at our imports that we had earlier, we actually pulled in binary cross entropy, and that's available from keras.losses. So we pulled that in, and we're able to say we want that binary cross entropy for the inputs and outputs, and we define that as our reconstruction loss. So that's one portion of our loss function. The other portion is just going to be this formula that loss function so that we can pass it through and optimize using this loss function, minimizing this loss function that we have. So we do this first by starting with the reconstruction loss. We're going to just multiply by 784 so that we're not working with the average value, but rather the full value, rather than the average over all the pixels. So we're just using this binary cross entropy. So far, we've been passing in that string as our loss function. But if you look at our imports that we had earlier, we actually pulled in binary cross entropy, and that's available from keras.losses. So we pulled that in, and we're able to say we want that binary cross entropy for the inputs and outputs, and we define that as our reconstruction loss. So that's one portion of our loss function. The other portion is just going to be this formula that we have here above. And we're going to pass in the z log var, which is going to be one of our outputs that we specified in our encoder, as well as the mean value that we have here. Sorry, we have the log, z log var there. And then finally that square of the mean value. And then we're just going to sum that KL loss on that final axis. And then the total loss is going to be the mean of the reconstruction loss plus that KL loss. So that reconstruction loss that we defined here, plus the KL loss that we just defined down below, which is this function that we discussed both in lecture and here in the notebook. So we're going to run those cells. And then once we have that total VAE loss, we can add on to our model by using this add loss functionality within Keras. We can call add loss and pass in this total VAE loss. And then we can just compile and specify our optimizers as well as the metrics we want to track. Once we do that, we can look a bit at our summary. It gets a bit intense with everything that we're doing, but we don't have to worry too much about it just here. And then we'll fit that to our X-train flat. So this is training our full model. The number of epochs we defined above as just 1. I'm going to pause the video here as it'll take about 10 seconds to run, and we'll come back as soon as that's done running. So that should have been a quick second to run, or a quick 10 seconds. And now we want to look back at the reconstruction error for our new model that we're working with, the variational autoencoder model. I want you to think whether that reconstruction should be higher or lower than the original autoencoder, without maybe reading what we have here below. I'm going to run this here, and we're going to see that we have a much higher reconstruction error. And the reason being that this latent space is built more for interpretability, that is sampling from a distribution, rather than being perfectly reconstructed to those original images. As now we're kind of sampling rather than taking the direct latent space that we learned. Now I want to plot out the latent space that we had. So we have our models. We're going to create a tuple that's just the encoder model and the decoder model so that we can pass that into our function later. And then our data is also going to be this tuple, which is x test flat and the related y test. So this is pretty large. I'm going to summarize. I'm not going to go through every line of code here, but I am going to summarize what the data is actually, or what the function is actually trying to do. So we have our encoder and decoder, as well as our x test and y test. And the first portion of our function is going to be to actually plot out in two-dimensional space, as we did with PCA, each one of our different numbers. So that's going to be the first portion. In order to do that, we need to get our z value. So we're going to get each of the predicted z values, and with those z values, we're going to also get their related numbers. So we're setting the color in our scatter plot according to that y test that they're related to. And then we have our two dimensions of z0 and z1 in that two-dimensional space. And those z's are going to be those random samples that we pull out according to what each one of those digits are. And then on the lower portion, so we're going to actually plot out two plots here. We're going to create a grid space ranging from -4 to 4. If you see that our limits, here our limit here is 4, passing into the function, or whatever our limits tend to be that we can pass into our function. Here it's -4 to 4. We're going to plot a bunch of values. Here n is equal to 30, so 30 different values between -4 and 4 on both the x and y axis. And we'll see for these different values of x and y, what is going to be, and recall, with our z's, we originally plotted out in 2 dimensions which numbers they're closest to. And we'll see this once the picture comes out. But now we're actually going to generate numbers using the decoder. So let's say our first value is -4, -4. Then for -4, -4, we're going to pass that in by using that xi, yi. We're going to pass that into our decoder and see what kind of sample it actually generates. You can think of the value being 0 and 2 or 0 and 3. And remember, these are supposed to be samples from something close to a normal distribution. So I'm going to, now that function's been initiated, I forgot to run this. We need to make sure that we have all that defined. And then we're going to actually plot the results. And this should make what I just discussed a bit clear. So here we have the different groupings. So we see for our purple here, which is related to our ones, those tend to be in the top left corner, which is -4 on the Z0 for our first dimension and Z1 being +4. And then when we look at the numbers generated, those tend to be ones. Whereas you see here on the bottom, that darker purple is the zeros, and here it's generating those zeros. Top right, we have the light green, which is associated with the sevens, and we see that that's predicting or generating sevens as well. So we can see this generative process. Then finally, in exercise 6, we want to train the variational autoencoder as well as the autoencoder for 10 epochs each, and then plot the reconstruction mean squared error as a function of the total number of epochs for each one of these models, and see which one seems to have more potential to continuously learn as it's given more computing time. So we have here, it's going to start running for 10 epochs. I'm going to continue running. I'm going to talk through what we have here because all we are doing is then running our variational autoencoder model for 10 epochs. For the autoencoder, we had that function defined in maybe video 1, I believe it was. I'm going to scroll all the way up. Maybe it was video 2 because video 1 was on PCA, where we defined this function here that trains AEE, our autoencoder, for a certain number of epochs. We don't have that for the variational autoencoder, so all we have to do is for I in range 10, fit that model each time for one epoch. Again, recalling that every time you run it, it's going to pick up where the last one left off. So each of these are going to take some time to actually plot out. We'll come back when that's done, and then we'll actually plot out the loss functions across each. All right, I'll see you in a bit. All right, now we have had our autoencoder as well as our variational autoencoder run for 10 epochs each. And we can look at the plot over time or over the number of epochs. And we see that there tends to be a plateau for those autoencoders, whereas the variational autoencoders are continuing to go down. You could probably run this a little bit further if you wanted, maybe 10, 15 more epochs for the autoencoders to really plateau. But we see that the autoencoders are fitting exactly and eventually are going to plateau due to the fact that they're fitting exactly, whereas the variational autoencoders continue to decrease and will take a little bit more time to get to that same reconstruction rate, probably never getting to that same exact reconstruction rate as we see with the autoencoders. Now that closes out our notebook here. And after this, we're going to get back into the lecture and discuss a different generative process, specifically GANs and generative adversarial networks. All right, I'll see you there.